Okay, so now we're going to learn the application of redox reactions. Okay, so we're going to look at how we apply this electron transfer that we've learned how to balance. And we're going to do that by looking at what's called a voltaic cell. Okay, I'm going to give you a lot of background here, and then we'll do problems in class. It's not as hard as it necessarily appears with all of this background information, and once we get to actually applying it, it's pretty straightforward. But going through the process of understanding it can seem a little confusing because it's something so different from what we've done before. So a voltaic cell is a device used to produce electrical energy from an oxidation-reduction reaction. So think about it. We had a flow of electrons, and if we want electrical energy, all we need is a flow of electrons. Well, we can get those electrons to flow by separating them into two separate containers, and we're going to learn how to draw a voltaic cell. We have what's referred to as the anode compartment, and the anode compartment is our oxidation reaction, okay? And the way we remember that is that they're both vowels. So oxidation occurs at the anode. The cathode compartment is the reduction half reaction, and again, we have now consonants, okay? So cathode is going to be our reduction reaction, and when we go through an example, this will make a little more sense, and then when we look at it again in class, it'll be pretty easy. Electrons always flow, I'll point this out here, from the anode to the cathode. Okay, so they flow alphabetically. So what we need to look at is something called standard cell potential. And so standard cell potential, which is referred to as E cell, and this little knot just means standard conditions, and those conditions are this right here. So it's the measured cell potential when the ion concentrations in the half cells are 1 molar, which means our ions that we have a 1 molar concentration. Our temperature is 25 degrees Celsius, and we're at standard atmospheric pressure, so 1 atm or 101 kilopascals. I don't need you to memorize those conditions. It's just important for you to know that if we were to change the pressure or change the temperature or change the molarity of the solutions, it would change our cell potential. So you'll always see this little knot, and that's just sort of saying, hey, our conditions are all the same. So a cell, you take the reduction reaction and you subtract it from the oxidation reaction. And that will enable us to calculate what is the voltage, and you learned voltage in physics, that's why we do physics first. You'll be able to calculate the voltage that we can produce by this chemical cell. So all reactions are written as reduction half reactions and read off of a table. And I want us to take a look at that table right now. Here's the table, and there's many versions of them. Most textbooks have a copy of them, and I will obviously make sure that you all have a copy of them. But it's they're all reactions here written with some sort of ion plus electrons gives some sort of product. Sometimes it gives a solid product, and sometimes, like it does here, it's an ion plus electrons gives a different ion. And you'll notice that there's a voltage that's associated with all of that. And here we can go all the way down. If you take a look at the numbers, we know things like lithium and barium and strontium and calcium, they want to be positive ions. They don't really want those electrons. So if we look here, we notice that their voltages are negative. As we move our way down, and notice that they're all reduction reactions, okay? Gains electrons reduced, okay? Every one of these is gaining electrons. We have to write them consistently. We write them all as reduction reactions so that we can compare them. If we look down at the bottom of our table, we notice here's fluorine, who really wants electrons, and so that voltage is positive. We look down at other things, and some are more complicated. They have more things involved, but we look at things. Gold has a positive, silver happens to be positive, iron happens to be positive. Typically, our things that are less electronegative are negative near the front or the top, and things that are more electronegative are positive near the bottom. So these cell potentials will enable us to calculate the voltage across the cell. All half reactions are written as reduction half reactions and read off the table, just like I showed you. And the table is arranged from less likely to be reduced, less likely to gain electrons, like I pointed out, to more likely to be reduced, more likely to gain electrons. Our things that are more electronegative are going to be near the bottom. the more positive the value is on the table, those were our ones at the bottom, the more likely it is to be reduced, the more likely it is to gain electrons. And the more negative the value, the ones that we had near the top, the more likely it is to be oxidized, the more likely they are to want to lose electrons, like the things we had at the top of the table. Okay, so for calculating standard cell potentials, we picked two reactions. And the two that I've picked for us to look at are a copper reaction and a nickel reaction. Okay, so here we have copper ions plus 2 electrons yields copper positive 0.34. Nickel plus 2 electrons gives me nickel minus 0.25. And I picked those two and I read them right off the table. So I just copied a little excerpt from the table for you right there. We need to determine which reaction will be the reduction half reaction and which will be the oxidation half reaction. I'm going to show you conceptually how to go ahead and do this, and then I'll go through the steps on the next slide. But what we need in order for a cell to work, in order for it to conduct a current, we need the overall voltage to be positive. And so this is really, really intuitive. We also need to reverse one of these two reactions. We can't have them both going the same direction because we need an oxidation reaction and we need a reduction reaction. Our table is only written as reduction reactions, which means we always are going to have to reverse one of our reactions the opposite direction. When we reverse a reaction, we reverse the sign. So if I want overall, when I add these two numbers together, to be positive, I need to reverse the one that is negative. And so what I'll end up doing here is I'll have Cu plus 2, which is aqueous, plus 2 electrons, yields Cu solid, and that's going to be plus 0.34 volts. But this one here, I'm going to switch it to an oxidation reaction. I'm going to switch it from being reduced to being oxidized. So I'm going to go ahead and write Ni solid becomes Ni plus 2 aqueous plus 2 electrons. And then, because I reverse the reaction, I can reverse the sign. The overall voltage of this cell, which I'll show you how to construct momentarily, is I just add these two numbers together. And I leave the positive in there, just like we did with exothermic and endothermic. We leave the positive and the negative because it makes it abundantly clear, and it's not like an oversight. So we do keep that positive sign in there. So all I have to do essentially is pick one of the reactions and reverse it so that my whole thing is going to be positive. This is a pretty straightforward one because my electrons are equal. So if I were to add this reaction together, overall, I would have Cu plus 2 plus Ni solid yields Cu solid plus Ni plus 2 aqueous. If I needed to multiply through to equal out my electrons, that's fine. I never, ever multiply these voltages. Never multiply the voltages. I only switch the signs. So even if I had to multiply one of these reactions through by 2 or 3 or 4, I wouldn't change these. And to me that makes it even easier. Okay. The half cell with the more positive reduction potential is the one in which the reduction occurs. Okay, that's going to be our cathode. So the more positive reduction potential. And the oxidation occurs at the anode. Okay, so that's what I told you, showed you earlier. So the more positive one, this was my more positive one, and I left that in the way that it was because it was already being reduced. I add the half reactions together, I make sure the electrons lost equals the electrons gained, and I calculate the standard cell potential. So it's always reduction minus oxidation. So plus 0.34 minus a minus 0.25, but you can do it the way I did it. If it conceptually makes sense just to look at it like this, that's fine. That's the same thing. We reverse the reaction, so we reverse the sign. It's the same thing as subtracting a negative 0.25. Okay, so these are your notes on what we just did. Okay, we knew which one to switch because we needed it overall to be positive. We knew our oxidation occurs at the anode. We added our half reactions together. Our electrons lost equals our electrons gained, and that's our overall cell potential. Okay, so here's our reaction, but now I want to show you how to actually draw visually a voltaic cell, because this is what we're going to have to do. The overall reaction is what I showed you just before. Cu plus 2, which is aqueous, plus Ni solid, yields Ni plus 2 aqueous, plus Cu solid. Oh, that's a typo there. That's a solid. Okay. Now, I'm going to have two containers, because in order for electrons to flow, I need to have them separated. I also need some sort of conducting metal, and very conveniently, my reaction is both metals here. Okay, and in order for my reaction to flow, I need to have my ions here. So this is in a liquid. Okay, but I need to capture my electrons. I need them to flow somehow, so I need to have a wire. So I'm going to connect these two pieces of metal with a wire, and I'm going to put my voltmeter there so I can measure my voltage. And what I'm going to do is I'm going to say, okay, this will be nickel metal, because that's one of the things that I need. I need nickel, that's solid, and I need copper, that's solid as well. So those are my two electrodes that I have. So here's electrode 1, here's electrode 2. My electrons are flowing from my nickel. My nickel is losing the electrons. Nickel is also my oxidation reaction, okay? So in solution here, I have nickel, but then I also need my nickel ions, nickel plus 2. And in this solution, I need my copper ions, okay? So essentially, I take one reaction, I take my nickel solid and my nickel ions, and I take my copper metal and my copper ions, and my electrons are flowing from the nickel. See, he's losing electrons, so my electrons are going this direction, and the electrons are going to the copper. I know that this is my oxidation reaction. That's the one I reversed. So I know that this side is my anode. I know that this is my reduction reaction. This is the one that I didn't reverse. And so this is my cathode. Now, you learned circuits, and we know, so in order to have a complete circuit, we need to complete this circuit, because it is certainly not complete. So my electrons could flow this way, but they're just going to get built up over here, and that's not going to happen. So we need a complete circuit. In order to complete the circuit, we need to put something here to connect these two, and we refer to this as a salt bridge. The salt bridge completes the circuit, because as the electrons leave here, this side becomes more positive, and so then this part of the salt bridge, if it's like sodium chloride, the chloride ions will dissolve in here in order to neutralize the charge over here. Same thing as the electrons come over here, this is going to become more negative, so the sodiums will dissolve into this side to keep it neutral. We know that the overall voltage of our cell was 0.59 volts, so I would read that on my voltmeter. So if I set this up with a piece of nickel and a piece of copper and the two ions, and the electrons flowed, if I put a voltmeter there, I would read the 0.59 volts. Okay. And the last thing is that as the electrons come here, they're combining with this copper plus 2, and as they combine, they become copper solid. So this electrode is actually going to gain in mass. It's going to increase in mass, and your cathode is going to increase in mass. As the electrons leave here, these are going to become more Ni plus 2. So this electron is going to lose mass.